Now in this faulted architecture you can see that 6 number of delay elements are being used. Okay, and this architecture is n times slow as compared to the original architecture. So since we have reduced the area, the cost is speed. Okay, we have to sacrifice the speed of the system. So whenever we try to optimize one of the parameter, that is power, speed, area, the one or other two parameters suffers. Okay, so now further we will reduce the area of this folded architecture, and we will do this by minimizing the delay elements that are used in this architecture. So the next topic will be register minimization technique, and so for this we have to follow a procedure, and that procedure is called lifetime analysis. So it is a procedure that is used to compute minimum number of registers required to implement a DSP program. So these registers are used to store data samples, or you can say variables, and there are two terms associated with it. And a data sample is said to be live or dead depending upon its status. So a data sample is live from the time it is produced, and it is called dead the time it is consumed. It is consumed. Okay, so we will be using these two terms exhaustively: live data sample and dead data sample. And these two terms will be used to calculate the lifetime of any data sample or variable. Okay, and the data sample occupies one register during each time unit. During each time unit, that is live. Okay, so during its entire life cycle it will be in one of the registers present in the system. Okay, okay, so one registers for one data sample at any given time. Okay, so what we have to do, find the you have to find the maximum number of live variables, number of live variables at any time unit, and this will be equal to minimum number of registers required to implement the DSP program. Required to implement the DSP program. So at any given instant of time, one register is required for one data sample. So suppose we have n live variables and n is maximum. Okay, so suppose this is different instant of time. At this time, suppose the live variable is 1. In this instance, it is 2, it is 3, then again 1, then 0, then 2. The maximum value is 3. Okay, so 3 registers are required to implement the corresponding DSP program. Okay, so consider a DSP program that produces 3 variables, variable A, B and C, and let A is live during time units, n is a set of 1, 2, 3, 4. Okay, and B is live during time units 2, 3, 4, 5, 6, 7, and C is live during time units 5, 6, 7. So a linear lifetime chart is used to graphically represent the lifetime of each variables. So we will use a chart that is called a linear lifetime chart. Linear lifetime chart that will be used to represent the lifetime of each variable. Okay. So we have to also ensure that the lifetime of variables from previous and subsequent iteration do not overlap with lifetimes of ABC. Okay, this is the assumptions that we have made to calculate the live variables, and we will be using linear lifetime chart technique. It is a graphical representation of lifetime of each variable. So the linear lifetime chart is shown here for this example that we have taken. And one convention is being followed, that a variable is not live during the clock cycle it is produced, and it is live during the cycle it is consumed. Okay, so for example, variable E, it is live during cycle 1, 2, 3 and 4. So it is given that A is live during time units 1, 2, 3 and 4. This means that it was produced in the 0th cycle. Okay, so during the time of its production we will not consider it as live. So it is, variable A is produced at 0th cycle. Okay, so it is not live at this instance, and 2, 3, 4. For the remaining period it will be considered as live, and at 4th clock cycle it is consumed. So after that it is dead, and for this cycle it is live. So it is produced at 0th clock cycle. So variable A is live during cycles 1, 2, 3 and 4, so it is produced at 0th cycle. B is live during the cycles 2, 3, 4, 5, 6, 7, so it is produced at cycle 1, and C is produced at 4th cycle. Okay, and to represent this on this linear lifetime chart we will draw vertical lines. Okay, so for A it is produced at 0th cycle and it is consumed at 4th cycle. Okay, so we'll draw a vertical line corresponding to A starting from 0 to 4. Okay, so at this point it is consumed, after that it is dead. For B, starting from 1 to 7, and for C starting from 4 to 7. So starting from 0 to 7, we have to calculate the live variable at any given instant of time following this convention. So starting from 0th cycle, okay, A is produced at this point, so it is not considered as live. So live variable is 0. No other variable is present at this point. During first cycle, now A will be considered as live, so live variable is 1, and B is produced at this point, so we will not consider B. During the second cycle, these two are live, so live variable is 2. During the third cycle, lifetimes of two variables, that is A and B, are overlapping, so again 2. At this point, A is consumed and B is alive, so total is 2. Okay, so we will consider A as live at this instance, and at this point C was produced. Okay, so we have not considered C at this instant. At fifth cycle, now C will be considered as live and B is also live, so two variables. And at sixth cycle, two variables. At seventh cycle, two variables. Okay, so this DSP program with variable A, B and C can be implemented using two registers based on this analysis. So one thing we have ignored at this point, and the thing is that DSP programs are periodic. This means that lifetimes of A, B and C from one iteration may overlap with the lifetime of the same variables from other iteration. So let's assume that the iteration period of the given DSP program is 6, and I will consider two iterations. Okay, and then considering these two iterations, I will calculate the live variables. So now for variable A, I can say that for any iteration L, it is produced at instance 6L plus 0, and it is consumed at instant 6L plus 4. Okay. Similarly, I can write for B, it is produced at 6L plus 1 and it is consumed at 6L plus 7. And for C, it is produced at 6L plus 4 and consumed at 6L plus 7. So we will use this formula to draw the vertical lines. And I have considered two iterations. So this is first iteration starting from cycle 0 to 5. Total number of cycles in iteration is 6. So L is 0 in this case. And this is second iteration starting from 6 to 11. L is 1. And you can consider 3, 4, 5, any number of iterations. Okay. So A0, B0 and C0 are produced in first iteration, and A1, B1, C1 are produced in second iteration, that is L equal to 1. So in this we have considered 6 variables: A0, B0, C0 for iteration 1 and A1, B1, C1 for iteration 2. And now we have to calculate the lifetimes of this 6 variable based on this formula. So starting with A0, for A0 L will be 0, so it will start at 0th cycle and it will get consumed at 4th cycle, from 0 to 4. Okay, so this dot represents that the variable is consumed now. And A1 L is 1 for this A1, so 6 into 1 plus 0, that is 6. So during second iteration it is produced in 6th cycle, and it is consumed at 6 into 1 plus 4, that is 10th cycle. So this is 10. So this is the lifetime of A0 and A1. Coming to B, B0, so produce at first cycle. B0 is produced during first cycle and consumed at 7th for L equal to 0. This is to 7. And for L equal to 1, B1 will be generated at 7th cycle in the second iteration, the 7th cycle, and it is consumed at 13th cycle. 6 plus 7 is 13th cycle. Okay, so it is consumed at 13th cycle. Okay, and C0 during first iteration, it will start from cycle 4 and it will end at 7. So C0 starting from 4 and getting consumed at 7. And for L equal to 1, C1, L equal to 1, starting at 10th cycle and getting consumed at 13th cycle. Okay, so getting consumed at 13th cycle. So you can also take third iteration, fourth iteration, and so on. Okay, but for this program, 2 iterations are enough. Okay, and 2 cycles of third iteration is also taken. So this much amount of cycle is enough. So now we will calculate live variables at each cycles. Okay, so at this point, live variable is 0. At this point, live variable is 1. Okay, A0 is live, B0 is just produced, so we will consider A0. At this point, third cycle, A0 and B0 are live, so 2 variables. At fourth cycle, A0 is live, B0 is live, 2 live variables. C0 is just produced. Okay, so we will not consider C0, so 2 live variables. Fifth cycle, B0 and C0 are live, so 2 live variables. At sixth cycle, A1 is just produced and B0 and C0 is live, so 2 live variables. During seventh cycle, A1 is live, B0 will be considered as live. We will not consider B1 as it is just produced, and we will consider C0, so 3 live variables. Okay. At this point, 8th cycle, 2 live variables, 9th cycle, 2 live variables, 10th cycle, 2 live variables, 2, 2, and 2. So now the answer is 3. So when the periodic nature of DSP program was not considered, answer was 2. And when we considered the periodic nature, and the answer is 3. So this means that we have to consider the periodic nature during lifetime analysis. Okay, and one way of doing this is draw n number of iterations for each variable, take n copies and draw the lives of the variable and determine the life cycles. Okay, so this process is very lengthy, and fortunately this periodic nature can be taken into account without explicitly drawing the lifetimes of several iterations. Okay, so you don't have to draw the lifetimes of multiple iterations. What you can do, you just draw the lifetimes of the variable for 0th iteration. So I have drawn the life cycles corresponding to the variable a0, b0, c0, and this is iteration number 1 starting from 0 to 5. This is second iteration. Okay, so in this case number of cycles that we have considered is greater than 6. We have considered 8 cycles, so small n is greater than capital N. Okay, so second iteration is automatically included. So for the first iteration, the calculation is as usual. You can directly calculate the live variables. Okay, so 0, 1, 2, 3, and 2. From this point onwards, that is from second iteration, you cannot directly include the number of live variables. Okay, so number of live variables at this point is 2. Okay, so what you have to do, you have to refer the previous iteration. Okay, so this is the first cycle of second iteration, so you have to refer the first cycle of previous iteration, that is 0th one, and you have to add the live variable present at this point to this value. So 2 plus 0 is 2. Now for 7th cycle, live variables is 2. Okay, and this is second cycle of second iteration, so refer second cycle of first iteration, that is 1. The number of live variable is 1, so you have to add 1 to this point, and the answer is 3. So this is how you calculate the lifetimes of variables of DSP program by considering their periodic nature.